Hello, everyone. Today we are going to talk about statistical process control, SPC. I will introduce related topics about SPC. SPC is a major statistical tool for checking the conformance of the product to their designed requirement, and it is the focus of this course. The major goal of SPC is to distinguish special cause variation from common cause variation and give a signal as soon as a special cause variation occurs. Then we need to define special cause variation and common cause variation. Before that, let me demonstrate a general production process. In general production process terms, material, component, subassemblies, information, and other necessary inputs into desired output in the form of products. Then the products are properly evaluated and monitored. Any problems found in the evaluation and monitoring will be investigated, and the process is further improved. The quality characteristics, QCs, of a product can be continuous variable or discrete variable depending on their data type. The values of QCs of a product are obviously related to the input variables of the related production process. Because it is impossible to list all possible input variables and uncontrollable input variables are involved, the relationship between the QCs and the controllable input variables has a certain randomness involved. In other words, variation. When we design a product or a production process, we usually set some specific requirement on the randomness. Variation can be divided into common cause variation and special cause variation. Common cause variation caused by uncontrollable input variables and inherent part of the production process and cannot be changed without changing the process itself. When only common cause variation is present in the production process, the process is considered to be stable in statistical control or simply in control. Special or assignable cause variation is a relatively large and systematic variation from the designed requirement. The examples of special cause are defective raw materials, improper operation of the workers, improperly adjusted machines, and so on. When special cause variation is present in the production process, the process is considered to be unstable, out of a statistical control, or simply out of control. SPC is often divided into two different phases. The goal of phase one is to properly set up a production process and make it run stably. In phase one, we conduct statistical analysis to figure out the relationship between quality characteristics and controllable input variables, and set the controllable input variables at some specific levels such that the QCs would roughly meet their design requirement. And then gather and analyze the QCs using an SPC chart. And if unusual patterns are detected, adjustment and fine-tuning of the controllable input variables of the process. We repeat such control and adjustment step until all special causes to be removed and the process works stably. Finally, a clean set of data is used for estimating the IC distribution of the QCs. Phase two, the goal of phase two is to monitor the process online to make sure that it keeps running stably. In phase two, manufactured products are sampled sequentially over time and observations of the QCs of the sampled products are monitored using an SPC chart. And the chart gives a signal once it detects a significant special cause deviation from the QCs. After a signal of significant special cause deviation is delivered, the process should be stopped immediately, and the special cause should be figured out and removed. Then what is the difference between phase 1 and phase 2 SPC problems? First, the size of the observed data in the phase 2 problem increase sequentially. Second, the distribution of the QCs is often unknown in the phase 1 problem. So this distribution is routinely assumed to be known, or it can be estimated from an IC data, in-control data, in the phase 2 problem. Because of these substantial differences, SPC methodologies designed for solving the two problems are also quite different. Now let me give you two examples of production process. First one is manufacturing process of cardboard cans. To inspect possible leak either on the side seam or around the bottom joint, 30 samples, each of which has 50 cans, were collected, and the number of non-conforming cans out of 50 counted as the table shows. Suppose that we construct a control chart as shown in this figure. Now the question is to describe the following concept using this example, like input, output of the production process, and what is quality characteristics in this case, and special tools, statistical tools for evaluation and monitor, variation, phase 1 and phase 2, what is in control and out of control. Try to describe this concept using this example. Another example is about deforestation detection using image data stream. These figures are about the tropical dry forest of Bolivia in 1986 and 2000. Suppose that we are interested in detecting the time of deforestation. We can sequentially monitor the image data stream that is available in every 16 days and give a signal that a significant difference is detected between the current image and the image taken in the past. The second example is a bit different from traditional SPC examples. Today, changes toward data-rich environment in manufacturing are accelerating the development of new SPC methodologies. Still, one common feature of SPC in big data applications is that observations of one or more longitudinal processes are collected sequentially over time and take the form of data stream in the sense that new batches of data keep coming over time. And we expect SPC to answer is whether the underlying longitudinal processes are temporally stable or how their distributions change over time. In the following lectures, we will discuss about traditional SPC chart, such as Schwartz chart, cumulative sum chart, exponentially weighted moving average chart, change point detection chart. Thank you.